And this is when it takes a while until Microsoft Teams says you are recording. Okay, perfect. All right, so today we'll continue on from lecture 3. And we'll again do the usual. We'll go through a quick recap of lecture 3. So lecture 3, we talk about the overview of microarchitecture. It's again the same figure that is like a super high level of a chip design. Again, super high level. There's not all the signal here. And we talk about how many cycles it would take if you do a multi-cycle architecture. So let's assume everything take 1 cycle and the 1 cycle magic memory, right? You would then need to fetch the code, perform the execution in the ALU, or go to the main memory to actually get the data and then do the write back, right? So it kind of ranges between 4 to 5 cycles, right? Depending on what we assume. And this kind of seems slow because we can pipeline the design. When you pipeline the design, essentially what happens is you increase the utilization. What do I mean by that? When you are running in the so let's say this is cycle number n. You can actually feed in the next instruction, n plus 1, instruction n plus 1, and instruction n plus 2 into the pipeline, right? And this way, you can have multiple instructions being processed in the pipeline manner. And to enable this, you need to add the pipeline register to make sure each pipeline stages store all the intermediate variable tied to that instruction, right? And then we also talk about, okay, we have pipelining. Can we do better, right? Can we pipeline into 5 stages to 10 stages, 15 stages? The answer is yes, and that's actually pretty common things to do, right? But even though these are common things to do, they are consuming power and die area. So if you are buying a chip for your computer, it's a perfect thing to do. But say if you want to just get the microcontroller that control your remote control for your air conditioner, right? You don't need the pipeline because I mean when I change the temperature like this, right? Which I'm gonna have to change it back, right? Do you care if it's gonna happen like 1 millisecond later? No, right? A slower machine is totally fine, right? Because my human response is not as fast even, right? 1 millisecond, I can't even move my finger that fast. I'm human, I can't move that fast. Actually, I'm pretty slow because I'm fat, right? But the thing is, there are workloads that demands high performance. There are also workloads that doesn't care about performance that much. I just need the functionality. So sometimes you might be okay with just multi-cycle architecture with no pipelining. I just have a really simple processor or simple microcontroller, right? Or I need a really, really high performance chip, right? So if you own a smartphone like an iPhone or Samsung Android or any Android phone, right? They are fast. If you didn't realize, those are actually even faster than most laptops that you can buy in 2010. If you buy the phone nowadays, like, it's really fast because you need the performance. The app that you're playing on your phone, right? These days, right? It's actually pretty advanced. The games that you're playing on your phone have a really nice graphic, right? So these requires compute power, so they demand deep pipeline to make sure the phone is fast, right? And we also talk about superscalar architecture, which we'll continue on talking about this in not next. I think is it next week? I think it's likely next week. Actually, we'll start. But today we talk about processor design, and then we'll talk about the branch prediction, and then we'll jump to superscalar architecture and out of order execution. So we also talk about data dependency, right? And I'm going to kind of skim over these slides a little bit because while these are important for Lab 2, we covered this last week. And for OPAT, we covered this last year. So at the end of the day, you can kind of measure performance using either things like wall clock time, a number of cycles required to complete an instruction, or another metric, instruction per cycle, right? How many instructions you can finish in one cycle, or how many cycles does it take to finish one instruction? Then you have to consider, okay, how do I measure latency? Right? Latency is the amount of time it takes to do certain task. If you want to send a message over, what's the latency, right? When you run the ping, when you ping another machine, those numbers are also latency. That's different from bandwidth or another things like that measure throughput. Throughput is more like given the unit of time, how much thing you can put it through. Latency is more like given that one thing, how much time does it take for me to get it over to the finish line, right? And we talk about the type of data hazard. Read after write, write after read, and write after write. In basically dealing with write after read, read after write. Sorry, read after write hazard. And with pipelining, right? With sorry, with pipelining, you can have data hazard for codes like this, where you have data dependency, right? You have previous instruction generating result for the next instruction. So you have to make sure, for example, in this case, the R3 is updated, and you have the updated value, which is the addition of R1 and R2 before you can process this instruction. Because in that case, you either have to stall, right? Wait until R0 is written all the way back to my register file. So I have the updated register file, right? You can insert bubble. In this case, you stall and say, hey, I have the instruction n right here and generate the R0 for n plus 1, right? So for the next cycle, I'm going to change the color here. Next cycle, let's go to here. N plus 1 stay here, and I send the bubble right here, doing nothing. Because at that point, R0 is still not in here. I'm going to have to wait one more cycle. Let me change the color here. Instruction n goes here, n plus 1 say, hey, I still don't have R0. I'm going to wait. Then you have to wait one more cycle from here to out of the pipeline. Done. That's when R0 is updated. Sorry about my cat sneezing if you hear that in the background. Then, now that n plus 1 have R0, the next cycle, you can then proceed. N plus 1 comes in here. Right? That's when you have stalling. And the condition is stalling when the unit that we're going to measure is distance. Distance basically means that if I need something from previous instruction, how far am I from that previous instruction? Because that tells me is that data on the register file already or not, or is that still in the pipeline and I have to wait? So that's the distance. For example, if I have instruction n plus 1, n plus 2, n plus 3, n minus 1, and n minus 2, right? If these things say, hey, I need R0. I need R0 from n. In this case, the distance is 2 because there's two jump, n plus 2 to n plus 1 to n, right? To get your instruction. And if the distance is within the decode to the write back distance, it means that that instruction is still in the pipeline. I have to wait. So you must stall the decode stage until the data is written back so that you get the correct value of the register. Oh, here, basically, this happened in the write back, right? The commit the value back to the register happened after the write back. So when does it say you resume an instruction? If you need from it, right? If you need from it after the write back stage, that's when the value get updated, right? So what is the performance impact of this? Every time you solve, you lose one cycle. So things get delayed by one cycle stalling. So let's assume the program with n instruction and s stall cycle. The average CPI, right? Instead of n instruction per cycle, how many do you have? You stall s more cycle. So you in total you spend n plus s, right? Cycle to finish n instruction, right? Over here before this, you spend n cycle to finish n instruction. So over here you get one instruction per cycle in a perfect world. In a not so perfect world, you get n, right, instruction per n plus s cycle. So you lose performance. You lose performance because you finish fewer instructions in one cycle. CPI or cycle per instruction is just inverse of that. So you change the denominator, that becomes the numerator, and numerator becomes the denominator. But you can see the idea, right? And the problem with this f, how long did you have to wait? Can be based on how many times things like raw hazard occurs. What's the distance with instruction that causing the raw hazard? So this is bad. This is bad, and we should fix it. And we can fix it with data forwarding. So when the first time R0 becomes available, that's actually right out of the ALU. So you can actually get that from the ALU, right? It's just like, why are you waiting until write back when your data is already available from the execute stage, right? Or sometimes it's actually available right at the pipeline register because you have that store in the pipeline register. So we can use this instead of waiting for the write back to finish, right? So we can definitely use this. The question is how? We forward the data ahead of time. Sometimes we call this data bypassing, but if you read textbook, you're gonna see the word data forwarding. So data forwarding basically allow you to kind of forward the data in ahead of time, right? Depending on where that data is, it can be from here, from here, from here, right? That's where you can retrieve the next piece of data. So when distance, when the distance is 1, you have the data coming from here into the decoder. Say, hey, I forward this new piece of data. You feel free to use it because that's the correct result already. I just haven't commit to the register file yet, but use that. It's a correct value. When distance is 2, you can forward this part to here, or if it's from the main memory, now you can forward this part to here. When distance is 3, you can then forward this part to here, or this part to here, right? So these things allow you to forward the data at a time, right? So that you have the data ready for execution and you do not have to stall, right? So what are the trade-offs with data forwarding? The benefit is you're gonna have fewer number of cycles, basically mean higher performance. Perfect, yay. The downside is these are complex, right? You will find this downside in lab 2. If you find lab 1 complicated, lab 2 will be a mess. If you don't like lay out things on like, okay, this has to be connected to this. We have to check the condition here before you proceed. Like draw a diagram of all the function calls that you're doing in lab 2 first. That would definitely help reduce the complication because it would allow you kind of to figure out, okay, how do we do certain things? And consider in a real process where you have like 30 or more stages, this can be really, really complicated. But what even more is what make things more even more complicated is branches, right? And today we'll start to dive into this concept called branch prediction. But before we go into that, let's talk about branches. So we need to talk about control dependence because we write code like this all the time, right? This is really common. You do if else or you do for loop, right? And these are something that the programmer use a lot, so the machine should support this. And it should support it as well, to the point that I can branch without hopefully stalling the pipeline a lot. But let's first go into the issue of like, how do we handle branches? Let's assume we have to stall, right? So when you have control dependence, you have to stall the pipeline. That's one way you can solve it. Another way you can solve it is you can kind of blindly guess, like, oh, okay, maybe you have to take the if, right? But that's bad as well, because if you have a true-false question on the exam and you say, hey, I'm gonna just blindly guess all the time, what's the likelihood that, what's the expected value of your grade if I blindly guess the true-false all the time on your exam? What's the expected value of your grade?
Like 50%.
Yeah, 50%, right?
Yeah.
And when you have to work on the exam, most of the time, let's say it's a true-false question, right? You will employ this strategy called educated guess, because you most of the time you read the question, like, I think that's true. I'm not 100% sure, but I think that's true. Or I think that's a false, so I'm gonna put in false because I'm 80% sure that's a false, right? So with that, right, with the educated guess option, computer does this somewhat as well, right? It needs to kind of predict, is that a true or false statement? Should I go into the if or should I go into the else part, right? You can do delay branching. This is in the MIPS R4000 processor. Oops, sorry. You can kind of delay the branch, right? And if you read the R4000 manual, it will tell you if you have a branch, if the compiler will find something to fit in the middle, so that you don't have to figure out are we branching or not. You can do something else. This is what the GPU, for example, is doing. It's called fine-grained multi-threading. We'll talk about this. Or you can get rid of control flow. Get rid of control flow. This is a technique called predicated execution. Or you can fetch both paths. And today we focus on just this. We focus on just this because this is a huge topic, right? Just the educated guess option is actually employed in modern CPU, so we will talk about how they do it. But before we begin, we have to talk about what information do we need, right? So when you have a branch instruction, it's going to be something like branch, if something like branch not equal or jump, right? These kind of instruction change what? It change the instruction pointer. When do I have to update the PC or instruction pointer? What stage in that? Fetch, decode, execute, memory, or write back? To fetch, right? You need a new PC. I need next PC to fetch. If I jump, I don't know what's the next PC. So you cannot fetch. But let's first talk about what information do we need. First, you need to kind of figure out, is that a branch, right? Unless you go into the decode stage. If you're in the fetch stage, you don't know what that instruction is. You know what instruction it is in the decode stage. So if you want to, for example, you have fetch, decode, execute, memory, and write back, right? And this is a branch. By the time you know a branch, what is in the fetch stage? Most of the time it's going to be PC plus 4, right? The next instruction. But if it's a branch, then can you fetch PC plus 4? Right? So that's the first question you need to figure out. Is this instruction a branch? And you better be able to figure out by the time you fetch, not in the code, right? By the time you fetch, you need to be able to tell, is that a branch? You then need to find the direction of your branch. Are you taking the branch? Are you taking the branch and jump? Or are you going to the next line, right? Because if you have a branch not equal to, let's say this is line number 2, you can first option is go to line number 3, right? Line number 2, then go to line number 3. This means you are not taking the branch. Or you can go to, for example, line number 20, right? This means you're taking the branch. So you need to figure out, are you taking the branch or not taking the branch so that you can get the correct line fetch. Then, if you are taking the branch, where are you branching to? Because sometimes this number is not known until execute or until memory stage. So you need to figure out, okay, if I jump, where do I jump to, right? You don't want to blindly jump because then you're going to run random lines, and most of the time you just jump to random lines, it's going to be a wrong line. So you need to know where do you jump to. So these are three information that you are required to actually handle a branch, right? So let's talk about the simplest form of guessing. Right? What would be the easiest thing to guess? That are not too bad. Anyone want to guess what the guess should be?
Just take one side, like jump.
Yeah, just take one side and jump. And which side is the easiest to predict? Because if you go back one side, right? If you take one side, either taken or not taken, that's fine. If you take the not taken side, where do you go to next?
PC plus 4, basically the next instruction.
But the simplest form of guessing is always not taken, right? Because I know that's PC plus 4, I can always do PC plus 4. Why would this might work well? Sometimes if you have a loop where your assembly would turn the loop into, so this is a loop body, right? So this is always jumping to here, right? And then there's a condition over here to exit the loop right here, right? In that case, this condition check, if you're always not taking the branch, you're likely to be correct because you're looping, right? And at the end of the day, you take this branch, and in this case, you can see that if you're not doing, if you're always not taken, then you're gonna be wrong here because it takes the branch all the time, right? So this might work well in some scenario, and this paper is one of the examples. Like, okay, let's actually transform loop so that it's more not taken friendly, right? For both if else and for loop. That's why you can do a easy guess. I'm not gonna take the branch, do PC plus 4, and it hopefully more than 50% correct. So PLDI is a top tier conference on programming language and compiler. So if you work in these kind of area, this is like this is where the best work in the world go to. These paper basically change the control flow graph so that it's more friendly toward branches. But the downside is a really static policy. Always not taken, always not taken. So you can write program that would definitely kill this policy, right? And if you're a programmer, doing it by accident is possible. You might write one program, somehow run fine, write another piece of program, almost the same functionality, just structured the branch differently, and now it's all screwed up because you all mispredict in the branch. Before we figure out like what's the policy to handle branches, let me motivate you on why branch are important. So you need to think about the cost of misprediction, because in a 5-stage pipeline, right, you know where you're jumping. Typically, you know that in the execute stage because that's when you do the condition check, right? In the execute stage is where you have to do the condition check, right? So that's the earliest you can forward the data, right? That's the earliest you can forward the data. If you're in the execute stage and you're trying to forward the data over, it means that nothing can be fetched and nothing can be decoded, right? So you're losing 2 cycles per misprediction. So let's assume you have 10% control flow and 80% of branch are taken, and we always do always not taken. Right? We always do always not taken. What's the cycle per instruction over here? I will do this one, you do the next one. So to easily do this, let's assume you have 1,000 instruction, right? How many cycles does it take to finish this? 10% are control flow. It means 900 are normal instruction. And 100 are branch, right? Out of all the branch, 80% are incorrect. This is incorrect. And 20 of them is correct, right? Because we said 80% of the branch are taken and we always guess not taken. So this is a really bad program for our always not taken policy, right? For the 900 instruction and the 20 correct ones, these would take 920 cycle, right? Because you finish one instruction every cycle, that's fine. If you take into account of the first instruction in the pipeline, 4 more cycle to fetch, decode, execute, memory, write back. The 80 incorrect instruction, right? Obviously, you need 80, right? 80 for that instruction by itself, plus 160 cycle for the bubble. So in total, what you're doing is 920 plus 80 plus 160. That's 1160 per 1,000 instruction. You take 1160 cycle. CPI is 1.16. So what's the CPI of this particular scenario? I have a totally different program with 10% branches are taken. What's the CPI? All right. Anyone got the answer for the CPI?
Yes, it's 1020 divided by 1000.
1020 over 1000, right?
Yes,
So what's that?
it's 1.02.
1.02. So this thing is much faster, right? How much? Around 12 to 14%. I didn't do the division, but it's quite a lot, right? So it's quite a bit faster. This means that if you do the easy thing, you're not gonna get a lot of benefit because when you change the program, things die. Right? Branch prediction turns into a really bad prediction, and you get a really slow computer. So let's make prediction better. There are multiple things we need to figure out to make it better. First, this is the easy part. Is this instruction a branch? So we'll talk about this first because it's the easiest thing. When you want to predict a branch, if this instruction is a branch, my observation is this. The instruction doesn't change itself when you run, right? Inside the main memory, it's gonna stay where it is. It's gonna stay where it is. Why is that the case? Most of the time, if you have if else on, say, if you have a if else, right? On line number 10, the next time you are looping or calling this function, where's the line for that if else? It's gonna be line number 10. It's a static information. So branch instructions stay in the same place. So you can use PC to predict if that's a branch or not. Because it's the same PC value that would map to a branch, right? So if the last time I see this program counters value, and last time I look at this and I decode, oh, that's a branch. It would mean that the next time I see the same PC value, this is going to be a branch instruction, right? It's as simple as that. If I look at the PC and last time I look at this PC is a branch, the next time I look at this same PC, it's going to be a branch because your code stay at the same place. The next thing that I guess the next easiest is find out where do you branch to, right? If you branch at line number 3, do you branch to line number 20 or 21 or 1000, right? Where do you jump to? So predicting a target of your branch is also not too bad because most branches, they jump to the same target address. Why is that the case? If you have a code that goes like this, right? And then loop back right here, right? Whenever you have branches, I'll go to the next line, right? Whenever you have branches like this, these things are the same location. If I take the branch, it go to one location. If I not take the branch, I go to a different location. In most cases, you will also know the target because it's the same target. Unless you do something weird like a function, not weird, but you do something pretty unique for this, like using a function pointer. How many of you use function pointer in C before? If you use it, that kind of change your target based on where the pointer is looking at, right? But at the end of the day, it's not going to change a lot, right? At the end of the day, you point to one or two functions. So there will be a case that you point to a different object or different function call or methods, but it is likely to be a subset of those methods. So most cases, you can store this target location into a buffer. Whenever I said buffer in computer science, it means a storage, like a temporary storage that stores something. So I store the target in this buffer called branch target buffer, right? It records last time I see this PC value, here's where I jump to. So I will start to build a mapping between PC and the target. right? I now have a relationship between PC and target. PC2, I see, will go to target number 2, right? PC1 will go to target number 1. PC3, last time I see PC number 3, it might also go to the same target number 1, right? They can be the same target because sometimes you do if or function call to the same location, right? And here's a general structure of the BTV. Let's say I want to build this thing. I'll start to talk about how can I build the thing. You have a program counter, so that's in your processor already, right? Then you have two things. One is the way you predict direction. Is it taken or not taken, right? That's the direction predictor. And then you have the branch target buffer that store the mapping between PC and the target, right? Then you look up, right? You have the PC, the program counter. So then you look up, hey, is my PC here? If it's here, what does it mean? It means I've seen this line before, right? If it's here, it also means it's not just I see this line before. The last time I see this line is a branch because I have the target somehow. It means that this is a branch instruction and here's the likely target, right? So you search the PC, over here it's going to be a target. And the PC would be used to index into this target, right? If you can find this, there are two options. You can either take the branch or not taking the branch. So if you take the branch, where do you go to?
Target.
Just target. If you're not taking the branch, where do you go to?
PC plus 4.
PC plus 4. So the result of this, whether you're taking or not taking, this is the direction, right? Direction becomes the select line. Are we selecting PC plus 4? Or are we selecting the target address which is forwarded from the branch target buffer? And then that becomes the next PC. So that's how you can build this. That's how you can build this. So then the remaining question is how do I determine the direction of my branch? And this is the most likely the most complicated part. Because the rest are static, you know the code when you compile, so you can kind of predict the target. This one, which is determine the direction, are we taking the branch or not taking the branch? This is likely the hardest part. It's like taking the exam, a true-false question. Is that true or is that false, right? We will do a 10 minutes break. Let's do a 10 minutes break. We'll resume at 10 or 10. And then we'll continue on to talk about branch prediction and how to deal with the taken versus not taken. All right. So we'll meet again at 10 or 10 past 10. And while when we resume, we'll do a quick Q&A up to 5 minutes, and then we'll resume the lecture. All right.
Yes.
Okay. So I'll see you all in about 10 minutes. All right. So any questions before we resume and talk about how to pick where do we go? Oh, not where do we go, but what direction are we going?
Yes, Professor, you talked about branch target buffer and direction buffer in the previous slides. I
Yes.
just want to ask that these two are hardware, or it is just created during the first branch in the memory. Like it is already in the hardware, like direction predictor and branch target predictor, or they are created in the memory during the first branch and then they store the address in that.
Okay. So the buffer itself is in the hardware. The way you populate things in the buffer, that's done when you run the program. Right? So to break down your question, which is a great question, this buffer are things in hardware already, but the way you populate so that you can do this prediction is going to be gradually modified inside the hardware itself when you run the application, right? Any other questions?
No.
Okay, then let me proceed. By the way, I think my bread is burning. Let me stop. Yep, it's burning. Uh, so to predict the direction of the branch, right? There are a few things that you can do to help, basically to help. The first thing that we are not going to talk about in detail today is involved in more on the compiler side. So you want to learn what the compiler can do. I guess check with me because I did not offer the compiler class definitely this semester. Last year me and Ajahn Yosavalai had the like a programming language / compiler class that we opened. But one thing you can do is to kind of, when you compile the code, right? What the compiler do, one of the things that they do is they analyze your code and do that optimization that they can do statically for you before you convert that into assembly. For example, you've seen earlier example that say, hey, if I always predict not taken, I can modify my code to be more not taken friendly or more taken friendly, right? Or there's another work that do something called BTFN, or if it's a backward branch like a loop, right? If you look at the loop, it's going to be structured like this. A code, right, go down, and then you loop back up, right? If it's a backward branch, just go back in the code, then you always take the branch. If it's a forward branch, right? If you are doing a forward branch where you either go to the next line or you jump to another next block in the future, then you always take the branch. You can also do those kind of policy. Or you can profile. If you're not familiar with the concept of profiling in computer science, especially in like compiler system and hardware, whenever we talk about profiling in this like more like a system and an architecture area, it basically means that we'll let the computer or the program running and we'll gather statistics. And then the policy will be guided by the statistics we gather. So let's say we profile for just a fraction of the program. Right? We run the program for like 0.001% of the entire program. Then we measure the statistics and then we apply the right policy. For example, we let the program run for like 10 rounds to gather where do you branch for each of the branch that you see. Then based on that, we apply the prediction because it's likely that the program would behave similarly most of the time. And when the trend changes, then we can profile it again whenever the trend changes. So you can do that. So these are static branch prediction, right? You do this statically when you compile the program. Or you can apply the prediction when you run. This dynamic branch prediction, which would be the main bulk of this lecture. So unlike you do the prediction when you compile the code, now you do the prediction when you run code in hardware, right? And in reality, it's a mix of both things, right? You can do static prediction and dynamic prediction and kind of like put together a really good prediction. So that most of the time, if you have if, else, or for loop, you are 97 to 99% correct, right? This is much better than 50% correct or 80% correct, right? It's so much better, especially with modern computer where the pipeline is really deep. By the time you're in the execute stage, you might be 12 cycles in, right? 12 stage in. So if you mispredict, you lose all that 11 stages of nothing. You lose a third of things in your pipeline. So you lose a lot of cycles. So you want to make sure the branch prediction is really good because it has high impact on performance. So you can do things like last time predictor. And you can do more things, more advanced things like a 2-bit predictor or 2-level prediction. We'll talk about this today. And we'll first talk about BTFN. So we'll go through this thing one by one. Let's talk about BTFN. So let's say you have a loop branches. As I showed earlier, you go back in the loop, right? And most of the time, if you have a loop, that's a non-zero chance and pretty high chance, actually, you take the loop and go back. Otherwise, you won't write a loop, right? As a programmer, if you write a code that loop only one time, do you even need a loop? Right? So most of the time, if you have a competent programmer, or most of the code that you run, the loop will go at least like 3 to 5 to 10 times inside the loop, if not millions of times. But in reality, this go around and around and around, right? So when you have loop branches, take the branch because you want to go through the loop because that's most of the thing you ended up doing. For other branch, do the easy choice. Don't take the branch. So that's BTFN. Take the branch if it's a loop. If it's not a loop, just go to the next line, right? You can profile the branch as well and use what we call pragma, right? So if you use, anyone here use OpenMP before? To do multi-threading. If not, then it's totally fine as well. But if you install OpenMP on your server, right, the framework allow you to annotate your code with the pragma in the C code. Let's say you have a loop for something, 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 right? And then you begin the loop. This is the loop body. If you have OpenMP, you can have this pragma. Pragma is like a hint. You can do pound OMP, and then the option goes in here. It basically gives the compiler the hint, say, hey, I want to invoke OpenMP on this loop to make sure every iteration of my loop will be done in parallel. It's really easy compared to using pthread, right? It's really easy to make your code faster through OpenMP, but the loop has to have certain condition to make it actually fast, right? Things like, okay, can I actually run each iteration of my loop in parallel? So these are what we call pragma. So there are people who propose idea on, for example, we can profile the program, run the program for a little bit and see where things branch out so that we can jump and take the correct decision. Then you use pragma, which is a keyword for a programmer to provide hints. For example, you can say if likely X, right? This is a pseudo code. It won't run, but conceptually you can do this. You can do like pound sign likely taken or something and allow the compiler to pass in that information to the hardware. This is like a programmer-based branch prediction. If you have a giant loop that you want to make sure it's predict correctly, you can do this. But it's kind of annoying, right? It's kind of annoying because you have to annotate everything. So as a programmer, you actually, at the end of the day, you might not want to do this because it's more work for a programmer, right? At the end of the day, you might not want to do this, but a side topic, right? Pragma can be used for multiple purposes. For example, annotate is this loop can be run in parallel, which would allow you to add the OpenMP based Pragma, right? That say, hey, this can be run in parallel, go take it and run it in parallel. Or you can send certain message to the system, right? And the good thing about Pragma is if it's unknown, you would do pound and something that the computer has no idea. It won't cause any error. You say, hey, I don't know about this hint. I just compile the code normally and treat the code normally. So you can add the hints in and it won't do anything if the computer doesn't know what that hint is for. Which is a good thing because you want to make sure the program still function, right? In case you port your code, you download a code that has OpenMP and you forgot to install OpenMP on your machine, it will still run the program. It won't run using OpenMP. But these are static prediction. We can do it dynamically, right? The idea of dynamic prediction is we use runtime information. Whenever we said runtime, it, as the name suggests, it's done when you're running the program. Compile time, it means that you're doing this technique or applying this technique when you compile the program. That's before you run. You write the program, you compile the program, and then you run the program. It's a different phase of actually getting the program to run. These dynamic prediction is runtime techniques. Many of the things we are talking about in this semester or this course will be actually applicable to most, if not all, program in this whole world, right? So if someone asks like, hey, what's computer architecture about? It's basically make computer faster, but for every single program, right? This is for the like I have a tough time explaining this to my colleagues who don't really know much about computer science that, hey, you can work on things that apply to every single application too by making computer faster, right? Or more efficient. And this is one of the things you can do, dynamic branch prediction, right? Why are they good? You do it in a runtime. The programmer has no idea this happened, right? When you write a program, when you write a loop, have any of the professor that are not teaching architecture told you that, hey, your loop has to be predicted to make it faster? Because no one, well, from the programmer point of view, they don't have to care, right? They don't have to care because if we do this good enough, like if we do a good enough job here, the CPU by default is going to be fast. So that people don't have to suffer thinking about how do I write my loop. So we want to do this really well. The goal is we want to do this really well. Today we'll talk about some basic technique, right? So the first thing I'm going to talk about is called last time prediction. Last time prediction. The last time predictor, as the name suggests, right? As the name suggests, what does it do? So anyone want to take a guess what last time prediction would do? If I see program counter and if that's the loop, what would the last time predictor do?
It will just predict according to the last prediction or the last jump.
So almost, actually, yes, it would do according to the last actual thing, not the last prediction, but the last actual thing that happened to that branch. And that's it. Simple, right? You need one bit to store. Last time, what did we do? If it's 1, taken, 0, not taken. So it's easy to implement this if you think about it. Each program counter in the BTB, in the branch target buffer, has one more bit. That's either 0 and 1. That becomes either taken or not taken. If it's taken, you take the branch. If it's not taken, you not take the branch, and voila, you're done. Is that good? Probably not. Well, is it better than blindly guessing? Let me ask you this. Are these likely to be better than just blindly guess?
Well, you are again guessing based on just one condition. So I don't think so that it will be actually better.
It should likely most of the time, depending on the nature of the programmer, right? But at least there's one type of branches that this would cover and it would work really well. And that thing is called a loop, right? Because if you have a loop, you're gonna go around a lot. So that would bring the accuracy up quite a lot just by handling the loop, right? So the branch target buffer in this case will store one more bit to store the direction, right? And this would actually become your prediction. And here's the state, right? So if you draw out the state diagram, so if you don't know what a state diagram is, please check it out what a state diagram means, because it is important in computer science and engineering that you know this. But the rough idea is this. I'm gonna have a node that represents the state that I am in. I can be, in this case, there are 2 nodes. It means I can be in 2 different states. The first state I'm in here, the first one, the blue one, is I'm gonna predict that this is not taking. I don't take the branch. Oh no, the blue one is taking the branch. So I'm gonna predict that I'm gonna take the branch. If I'm in the red state or the red node, I'm gonna predict that I'm not gonna take the branch. The state diagram would involve how do I transition so that the next time I see this branch again, I know what should I predict. So let's use last time predictor to explain the state diagram here, because we can transition to a more complex state diagram, right? So if you are in the predict taken, like this current cycle, I have a branch and I want to predict that I'm taking the branch. If you actually not taken, then you transition, right? You transition to, hey, next time I'm not gonna predict taken, I'm gonna predict not taken, because the last time it's not taken. If I'm in a predict taken and in actuality, like in reality, it take the branch as well, I stay at the same state because I'm correct. Yay, right? And then if you are in the not taken state, in the red state, there are 2 things again that can happen. If in reality we take the branch, then you go to the blue state because it's take the branch. So the next time I'm gonna predict taking the branch. If you're in the red state, not taking the branch, and in reality, you're also not taking the branch, you stay there because the next time you're going to predict also not taking the branch, right? Any question about the state diagram? Then let's go through some example. What's the accuracy of this? Let's assume initially you are in the taken state, predict taken. So the accuracy of the first one is if you're in the predict taken, correct, incorrect, and then you transition to not taken, right? Correct, incorrect again. So you get basically 8 out of 10. Your loop behave like this. You'll be correct, correct, and not correct. This would be 10 over 11. By the way, I have one extra t by accident. There's actually 11 branches here, so it's 10 out of 11. But if you're in this scenario where you write a code that looks, for example, something like loop. In here, in the loop body, you do if x mod 2 equals 0, right? You do something and then you do x plus plus. Every time you go through this loop, you're gonna flip what you do, right? Because it's just check if x is divisible by 2 or not. And you keep incrementing x, so it's gonna be taken, not taken, taken, not taken, taken, not taken for that PC, the PC that points to this if instruction, right? So in this case, you're pretty much doomed because you're gonna be correct, then not correct, 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 not correct. So you get 9 out of 1 out of 10, right? So now your accuracy is dropping like crazy, right? So that's an example of how good things can be and how bad things can be. This is kind of like a bipolar policy where it can be really good or it can be really bad because we are not really adaptive, right? So how do we implement this? So now there are two things I'm going to add here. The first thing is I'm going to make sure last time predictor is there. And secondly, I will make sure that my branch target buffer is a little bit more space efficient because I don't want a giant table to store every single program counter ever, right? So I'm going to have a PC that divides things into the tag region and the index region. So are you familiar with the tag and the index if you take any things like computer organization or caching before? It's the same as the cache. So for OPA, this is the same as the tag in the cache or the index in the cache. But for Muhammad, have you seen this before?
No.
Okay, so if you haven't seen this before, right? Basically, you can break down the program counter in the binary format, right? You can break down into two different regions. One of them I would call this a tag. The other one I call this an index, right? Basically, it's just like, for example, it's 1110011. I will break it down, right? And because let's say this program counter is incremented by 4, which means that I don't care about the last 2 bits because I'm gonna make sure that that's gonna be divisible by 4. So that's gonna always become 0 and 0. So I don't care about those. Then I'll use maybe the last 3 bits for the index and here for the tag, right? Why do we do this? Let's say I have this giant branch target buffer. I have this giant branch target buffer. If the branch target buffer is 1000 entry, if I had to search every entry for my PC, how long would that take?
1000 cycles.
Well, you can kind of like do the binary search a little bit, right? But it would take a while. So the key here is it's gonna take a while. And inside your pipeline, can you afford to take that much time? No, you can't just simply say, hey, I'm gonna add 7 cycle or 8 cycle or 1000 cycles. You cannot. And so you need to be able to look this up really quickly. That's what the index is for. So are you familiar with the concept of a set in math? So think about it this way. This giant table is divided into multiple sets. Let's say it's set number 0, set number 1, set number 2, set number 3, right? This is a math, like think of it as a mathematical set, like definition of a set, right? What does a set do in maths? It collects items, right? It collects items. In this case, what does it store? It stores multiple tags inside the set. And the ID, you use the index for the ID. So in this case, I have 3 index bits, right? It basically now means that if the index bit in this case 111, right? I don't have to search in this set. I don't have to search in this set. I don't have to search all the way here. I just only have to go to set ID number 7 because I guarantee it's going to be there. I use the index bit to tell that by default it's going to be in that set. Then to actually check if my program counter is there or not, I use the tag. The tag becomes the key. If the key is there, then it means I have the program counter. I have the program counter, right? So let me erase everything here to make it more clear because I'm going to animate through this. The index, again, as I said, will point to the correct set. I just set out the index becomes the set ID in the branch target buffer. And once you're in here, there'll be multiple tags like tag 1, tag 2, tag 3, tag 4, tag 5, tag 6, right? We then use the tag and compare against all of this. So you reduce the number of comparison that you have to do because instead of comparing every single tag in this giant table, you just now have to compare to all the tags in that set, right? All the tags in that set. Then the first thing you do is, okay, is the tag match? Is the tag match? If it match, it means that I have my program counter in the table. I have PC in the table. Then if it match, I would look at the history table. This is the 1-bit information, right? Taken or not taken, that's the state. I'm going to predict if it's 1, taken the branch. If it's 0, not taking the branch, right? Then that becomes the bit for you to send in either the target, right? If you take, let me write it this way to be more clear, right? If this is taken, then you forward the target address to next PC. Or if it's not taken, I'm going to use a different color. If it's not taken, right, not taken, then I'm going to forward PC plus 4 as the next PC. So this way, I have a structure that allows you to quickly search. So that's the first benefit. Quickly search. You just go to the index bit. So you reduce the number of search thing that search number of items you have to search, right? Then you also have the history table. You have the way to predict, are you taking the branch or not taking the branch? Lastly, you have the target store as well. So with this one structure, you have everything. With this one table, you have everything. So it's simpler. It's faster to search. Why faster? Think of it this way. In your high school year, right? For example, you might be breaking down into multiple classrooms or your homeroom class, right? Let's say you're attending high school or middle school, right? There'll be multiple students per year. Then the way they break it down, at least for the homeroom class or the class that you gather together, right? Then you'll be breaking down by different class number. That's the index, right? For you, if you want to search, for example, for a kid in the whole year, if there's no way to break down each of the classroom, you'll spend a while, right? Because you have to look everywhere for that kid. But if you have a classroom as the ID and say, hey, that student is in class number 5, then you just go to class number 5 and search. It's going to be faster for sure because there are actually fewer people you have to search. Same concept here, right? So that's the gist of the last time predictor, right? Then I'm gonna go and transition into the a little bit more complicated 2-bit counter. So let's actually put in some we call it hysteresis. It's called 2-bit counter. Right? And the way 2-bit predictor is working is actually, let me introduce the paper that talk about the 2-bit predictor first. There was This was actually published in ISCA 87, right? 1980, not 87, 81, my bad. And the paper is a pretty seminal paper. This is done by James Smith at the CDC Corporation. Back in the day, the CDC Corporation, think of it as this one big company that make supercomputer. So it's kind of like the Intel of modern day. But back in the 80s, there are multiple companies. If you look back at the history of computer, right? Architecture is one, if one of the oldest field in computer engineering, if not the oldest field, because we built computer. If there's no architecture, computer doesn't exist. Throughout the history of time, there are many companies that try to compete for, we should build a computer this way, right? It's kind of like IBM of the 90s, where they come up with the personal computer and also server computer, right? And then Apple, right, that comes with its own version of the Mac computer. So CDC is another big company that built computer. One of the engineer and researcher over there write a paper on this is a study of branch prediction strategy, right? And one of the key things from that paper, right, if you read the paper, you see that one of the key things that it introduced this concept that last time predictor, as you seen earlier, if it's true, false, true, false, true, false, true, false, not true, false, taken, not taken, taken, not taken. Somehow I think about taking an exam. Taken, not taken, taken, not taken, taken, not taken. Then it collapses, right? You get zero accuracy because of just one different outcome. So that's bad in a sense, right? Because sometimes your program can be a little bit unpredictable, right? So in that case, the solution for inside the paper, which is, by the way, is 40 years ago, that's when we still trying to figure out how to build a computer, right? So this is pretty advanced when we consider, hey, branch can happen and branch can be bad. That was back in the day when, hey, circuit can be bad. We should figure out how to wire things together, right? So it's a different research problem than what we consider nowadays because of the advance of technology, right? But the solution in that paper is, hey, we can add the hysteresis to the predictor, right? Add one more state, one more bit. Because again, back in the day, your machine cannot afford to have a lot of bits. Anyone here use a computer in like year 2000? Or maybe 2005? So okay, let me put it this way, right? If you buy a computer in the 1990s to 2000, you are talking about a few megabytes of memory. You seen the floppy disk, right? That disk that can only store 1 megabyte of data. Back in the day, we are talking about like kilobytes and megabytes of memory. So one bit that you add costs a lot, right? That one single bit costs a lot. So the paper said, hey, let's add one bit. Say, hey, let's add one bit, add more cost to the machine, right? And the benefit of this is like, okay, you add just one more bit, right? But you add 4 more state or 2 more state to your outcome. So you can kind of have a longer history, right? So the 2 bits would use to track the history. So your prediction will not change right away if you do one single misprediction. Sometimes we call this bimodal prediction, right? And here is the state of the 2-bit predictor. Specifically, this is called a saturating counter technique for the branch prediction. Saturating counter it's used in many types of application, and you can use this same counter for branch prediction. Saturating counter is like a hardware design that allows you to count up and count down. And over time, when the reason why we say saturating counter is if you hit the ceiling or the floor, it won't count up. It will keep staying there. So if you say you are at number 3 and you want to count up and you only have 2 bits, it will stay at 3. If you add 0 and you have 2 bits again and you want to count down, decrement the number, it will stay at 0. So that's a saturating counter. It saturates at the top or at the bottom. So you use this for the prediction. Now you have 2 bits, right? So you can have 4 states. The state for 0, 0, I will call this, I'm going to predict taken, and I call this strongly taken. Why strongly taken? I have a firm belief, because I've seen so many taken branch, I have a firm belief the next one is going to be taking the branch. So this is strongly taken. And this is called weakly taken, right? The weakly taken state means that I'm going to still predict taken, but I don't have any belief anymore, because the last time the branch here that I seen is actually not taken. So I don't believe that, I don't have as much strongly believe that this is going to be a taken branch, but because I have to make a prediction, I will still say maybe it's a taken branch. Then you have the weakly not taken state. Similar to the weakly taken, last time is taking the branch, but I still am going to predict that this is not taking the branch. And this is strongly taken. So if I want to put the state name into the analogy is, if you have to do a true-false question on the exam, strongly taken and weakly, strongly taken and strongly not taken is when you have like so much confidence that it's going to be this choice. And the weakly taken and weakly not taken is like you maybe have 60-40 chance or 70-30 chance of this choice. Right? It's likely to still this choice, I guess, but I'm not as strong in terms of my belief. So the way you transition the state, if you have that assumption, is this. If you're in the strongly taken and the reality, the loop or the branch is taken, you stay there because you're going to keep your firm belief. If not, then you transition into the weakly taken because I predict it's going to take the branch, but in reality, the code doesn't take the branch. So I'm going to still keep predicting taken, but I don't have as much confidence anymore. Then if you're in the weakly taken, and it take the branch, then you have more belief into, okay, maybe I'm correct. I'm going to keep predicting taken, and I'm going to transition back into strongly taken. But if you're in the predict taken, which means you're going to predict taking the branch. In reality, you're not taking the branch and you say, hey, I don't believe in myself anymore. I'm going to predict next time that this loop will not take the branch. If you're in a weakly not taken, but the loop, in reality, the if else or for loop take the branch, then you transition back into the predict taken in the weakly taken state. And you do this for all the 4 states with the same logic, right? So what's the performance of this when you have these 3 patterns? So let's assume, that we start at strongly taken. The first one, I'll do the first one for you. If you're at strongly taken, this is going to be correct, right? Then the first one will be incorrect. You transition to weakly taken. The second one is incorrect because you transition to weakly not taken. Then it's going to be correct, and incorrect again at the end. So you are at 7/10 in terms of accuracy. It's going down, right? From 8 out of 10 to 7 out of 10. The second one is correct, basically correct until the last one. So you're again at 10 over 11. But the key is here. Correct, incorrect, you're in the weakly taken. Correct again, you're in the strongly taken. Incorrect, correct, incorrect, correct, incorrect, correct, incorrect. So you have 5 over 10. Much better performance, right? So generally, if you do something like this in a real program, in the paper kind of report that if you run a real program, you're getting about 80 to 90% accuracy, which is not bad, right? 80 to 90% accuracy is not bad. But if you ask this question, is this good enough, right? Is it good enough? It's actually not good enough. So the reason why they are not good enough is you have a lot of if, else, and for loop in your code. If you just go line by line by line, most of the time you see if, else, and for loop everywhere. Maybe roughly 10% or 5 to 10% of your code are these instructions or function call. Function call is another branch instruction because you jump to that function, right? But you know that you're definitely taking the branch because you definitely have to call that function. The program counter has to change to that function. The fetch address is not determined after n cycles. So let's say you can fetch m instruction per cycle. So if you are doing advanced processor design, you can actually process multiple instructions in a cycle. So let's say that's m instruction per cycle. Your misprediction will lead to n multiplied by m wasted instruction slot. That's a lot of instruction slot being wasted, right? So that's a lot. So are you still with me? I think let's take a break because we're going to transition into another more advanced topic. We are transition from the 1980s to 1990s. So we are now transitioning to the 1990s and late 1990s, right? Into like a modern day Intel processor. Let's talk about, yes.
Yes, I have a question.
Sure.
If we just increase the bits of the counter, like shifting from 2 bits to 3 bit counter, will the accuracy will improve more, or it will saturate at a certain level?
It does, and it does also saturate at certain level, right? So you can keep adding these bits. That would have longer history. So in a real processor, they will have longer number of bits in here. Right? In a modern machine, you also have longer bits, and it would kind of represent something similar, but not exactly this. Not exactly that state diagram that I show you, because sometimes you kind of jump from one state to another. It depends on how you design it, right? But the key here is it's gonna saturate. So you might want to take into account of not just the history of what has been done earlier, but maybe the history of all the branches of things like that. So we're gonna kind of transition into a 2-level prediction part of the lecture, right? So let's take a break. Let's resume at 11 o'clock before we transition into the last topic that we're gonna cover today, right? So let's do a break. We'll meet in 5 minutes, all right?
All right.
All right. So it's 11 o'clock. So let's resume. I think we are kind of behind on the lecture. I still have quite a bit of content to cover. I think we definitely have enough time. So the next question is, now that we have 2-bit predictor, right, can we do better? And here are the two main observations that works in the years 1990s observed. The first thing is, one branch outcome, right? There's a correlation between one branch outcome with another branch's outcome, right? There's a global correlation between all the branch in your program. If this is true, it's gonna likely to cause the next branch to be more likely true or more likely false, right? So it means that it would take there's going to be more tendency to take or not take the branch, right? Second observation is a branch outcome is correlated to the past outcome of the same branch, right? Of the same branch. So we'll go through this one by one. The first one is, how can we take advantage of global branch correlation, which is something like this. So here's a simple example, right? If this is your code, the first line, if condition 1, a equals 10. Then the second line says, if a equals 0, if a equals 0, do something, right? It means that if condition 1 is true, are we ever going to take that if, the second if?
No.
No, right? So if this is true, this will become false, right? If this is false, then in this case, we don't know, depending on the value of a, right? So that's a global branch correlation, because things that you do in a one if-else block impact the variable that comes into the condition check of the next if-else block. And so much of your code would behave that way. Sorry, my cat is running all around me, and I don't know where she is now. Wait, give me 1 second. All right, she went upstairs. Sorry. So if the first branch is taken, in this case, the second branch is also. If first branch is not taken, the second branch is also not taken. So how do we detect this pattern, right? How do we detect this pattern? The idea is keep more history, right? So on top of tracking the outcome of each individual branches, what you can do is, well, you can detect the global information of taken and not taken history. And we will call this local history register. Local history register, right? And the branch prediction will be made based on the outcome of the same global branch history. And I'll show the example of this, right? I'll show the example of this. Basically, the global history register will be used to index into my pattern history table. And this is a paper in by a technical report in 1993, where the title is Combining Branch Predictors, another seminal paper that talks about how to design a branch and how to do branch prediction. So here's the overview. There's a new thing that we add, the global history register. It will have certain pattern. Let's say 1 mean taken and 0 mean not taken. The global history register will be just pattern of 0 and 1. In this case, it will mean that the last time is not taken. The one before the last time is taken, not taken, not taken, taken. Basically, it will mean something like this: not taken, right? And this is the last branch that we keep track. And this is the oldest one that we keep track. When the new one comes in, let's say the next one is not taken, you then push everything and kick out the last guy. So that is how the register works. And we use this to check into what entry that corresponds to this particular pattern, because this GHR would now tell, okay, the last time I see this particular pattern, taken, not taken, not taken, taken, not taken, what happened to my branch? Now it would correlate with the same exact pattern of branches that I see with this GHR history, to hopefully you can integrate the global information into this one specific branch. And let's go through some example to make it more clear, right? So here, let's go through this loop. Example number 1 and 2, right? In this case, right, let's assume for the loop, if you take the branch, you exit the loop. If you not take the branch, or actually not take the branch, if you not taking the branch, it's exit, and you take the branch, you loop. If is true, you not take the loop. If it's false, you take the loop, right? So for this example 1, what is my pattern? I first go in the loop, right? So you take the branch, take the loop. Then in that case, if I is less than 3, I'm going to keep resulting in true. So you're going to do not taken, then followed by this if, right? Then not taken again. Then you do taken, right? Because it's a loop. Not taken, not taken, taken, not taken. And now I is 2. So this becomes taken. Taken, 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 because I is now 3. Taken, taken, taken. So this first loop, this I is 0, I is 1, I is 2, I is 3, I is 4. And then not taken at the end, because I is now 5, you exit the loop. So that's my pattern, right? And this is the same thing. So I forgot that there's one example. Basically, the pattern of this whole loop is taken, not taken, not taken, taken, not taken, not taken, taken, not taken, 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 taken. So that's my loop. That's my loop. With this, right? With this, each one of these loops, let's say this is program counter 10. This is program counter 20. This is program counter 30, right? So there'll be 3 different entries for the program counter. Then you use the GHR, which represent this pattern, right? This pattern. And in this case, let's just assume that taken is 1, not taken is 0, right? And let's say the GHR is 4 bits. Let's say the GHR is 4 bits, and you're trying to predict this one. You're trying to predict this particular branch, right? If the GHR is 4-bit, when you're trying to predict that one branch, the value of GHR will be 1001, right? So then this is GHR. Then in your pattern history table, which is basically the table that collect here are the pattern of each of these particular branch, right? you will then look at the corresponding index. In this case, 1001, and in there there'll be another level which predict, right? In the next week, we'll go through a detailed example because we don't have enough time this week to cover this. But over here, there'll be another like counter basically that keep track of each of these PC. But instead of collecting the PC and use it as the index, you use the GHR. So in here, it will be another counter that it can be like something like 111, and let's say this is taken, that it would predict taken. If it result in not taken, then you predict not taken. Why is this good? It basically allow you to make this one prediction, right? This one prediction based on the pattern that you see earlier, rather than just the PC. So rather than just relying on the program counter, then you use the pattern you see before, right, to predict. Hey, what do we do here? It allows you to correlate these different program counter into one single prediction table. And we'll go into the detail of this next week, right? With a small example. But before we go to the detail, right? What else can we do? You can add more information to the predictor, to the global predictor. For example, right? I kind of want to cover what else can we do for the branch prediction. And when we do a recap next week, I'll go through the example so that you have the high level idea first. You can do something called G-share prediction, because earlier on, right, if you have the example here, it only takes into account of the GHR, the pattern that you see, right? And you might be asking, where's the program counter in here? It's not here, right? It's not here. So the two-level global history register doesn't take into account of the program counter at all. But you might have realized, right? You might have realized that the program counter is involved in the prediction process because it matters what branch you are predicting, right? So what else can we do? You can add the program counter as a part of the information. And the G-share prediction is another branch predictor paper that try to integrate program counter into this process, right? So we use the GHR and you XOR with the program counter to combine the two information together. And this is how it's done. So you have the direction predictor. This is a pattern history table, right? And you then XOR the PC with your GHR, right? So now the XOR of the program counter and the GHR becomes the index into my pattern history table. Pattern history table basically will have this the history, right? History of the branch outcome of these particular index. So this allow you to integrate program counter into the global history register. All right. What else can we do? What else can we do? Another thing we can do is what we call local branch correlation. Basically, you create the branch outcome by using the correlation of the past outcome of this same branch, And here's how it works. The goal is we want to associate the outcome with the history of the same branch. And this is one of the seminal paper in Micro 1991. It actually turns into like a idea from this paper turns into the actual predictor in the processor. There's a paper called Two-Level Adaptive Training Branch Prediction, proposed by Ye and Pat. And if you've seen this name before, Ye or Pat is one of the selected paper that I have on your review, right? That talks about prediction and trend for future architect that was predicted back in 2000. Also, Yale Pat was my advisor as well. He made a lot of seminal work on this direction. And also then follow up with a lot of seminal work on things related to how to make the critical part of the program faster, how to make multi-threaded program faster. All right. So the key idea is let's add this. And unlike the global information that use the global history register, then let's add this local history register, right? So the first level, you have a set of local history register that has n bit that correspond to either taken or not taken. And then the program counter of the branch are used to index into this LHR. So think about it this way. Global history register, the earlier idea is one single register, one single value that kind of integrate every single branches, right? And somehow you don't have enough of that because in your code, in your program, so many branches that are going on in your program. So let's expand this a little bit. And then instead of having the GHR, then you have the local history register. Local history register, and you use the program counter to index into these register, right? So it would collect multiple program counter that map to the same index. And then for that particular index, it works kind of similar to the global history register, which is basically look at the past outcome of the pattern that map to this one index, right? This one index right here. Is it taken, not taken, taken, not taken? To be n bits corresponding to n previous branches that map to this index. Then it can be used to map to the second table, which has the history, right? In this case, it's just a 2-bit saturation counter. Basically, it's 2 bits that I showed earlier. The strongly taken and weakly taken, strongly not taken and weakly not taken, to predict, hey, what should be my outcome, right? So this is another idea that can be applied, right? That can be applied to your processor design. Again, I'm going to go through the example with a code, right? With a code that is the same code that has this taken, not taken, not taken, right? This same pattern, we'll see how it evolves and how the prediction changes over time. And then not taken at the end, right? So we'll see how we keep track of this on the table and how it shifted over time. And once the table finish, I guess, profiling phase, like basically trying to make sure I have all the information on my program, then the accuracy will go up really high because it already records the previous pattern. And the shift in the pattern would be gradually recorded without impacting the other things you're trying to track. Right. So that's where the many of the work on branch predictor was in the 1990s to early 2000, right? And I have to admit that afterward, there's not a lot of branch predictor paper, right? Because with these techniques, you're getting like 95 to 97%, which is really good, right? The rest are either more or less engineering solution, which kind of like tune how we want to adapt this idea, or there's another set of papers that came out recently that looked into container and serverless computing and has been shown that all the ideas in branch prediction turns into fire. It's a dumpster fire because when you run serverless, you run functions quickly and then you switch to another container. So there's no way for you to collect history at all. So your branch predictor performance dropped significantly. And it was like there was a few papers that came out a few years ago in 2018, and it's still an ongoing research topic because things fundamentally change. The way you compute fundamentally changes. So the hardware should also adapt to the new way that the software changes, basically the new software direction, right? But then let me kind of wrap up today's lecture before we kind of like leave the last 30 minutes on talking about the projects and also talking about potential things you can do for both the project and anything that's related to the lab, right? So other advanced technique involve things like, for example, tournament predictor. This is IEEE Micro in 1999. This is designed in the Alpha 21 to 64 microprocessor, another high impact processor design from Alpha. And these days you don't see this machine anymore, but many of the things that are designed onto your processor, onto their processor, make a lot of impact to modern day processor, right? So the way tournament predictor works is you've seen local version of your predictor and the global version of predictor, right? The one that used GHR and the other one that used the LHR, the local history register, and integrate the PC to that. So the tournament predictor is not that complicated on top of this. You pick the better one. You have both of them. You add both of them, and then you pick the better out of the two, depending on where and when you're trying to make a prediction, okay? And as you can see, things get more and more complicated. There's another high impact paper in HPCA 2001 called the Perceptron Branch Predictor. So over here, this paper actually just got the Test of Time award a few years back, right? The award basically would given to papers from at least 15 years ago that make huge impact to both academia and industry. So this paper got the Test of Time award by the committee. I think I forgot the year, but I think it's likely 2018 or 19. I think it's 18, but I don't take my word for it. Definitely in the range of 2017 to 19. So the idea is, instead of using this local and global predictor, let's use Perceptron. What is Perceptron? Basically, right, individual branches are being assigned weights, and you use supervised learning in the form of Perceptron to adjust the weight based on the outcome of your branch. And if you happen to use Samsung mobile phone, it actually, the branch adaptation of this branch predictor is used on Samsung CPU. So you can see that many of these papers' impact are now prevalent in modern CPU. Right, both Intel, ARM, you need it. Basically, you need to use this branch prediction, and you keep seeing paper from Intel and this industry on branch prediction because we still keep wanting to invent new things. So these are some of the open-end. Well, these are all topics, so I'm not gonna directly say open-end. These are all like 1990s to early 2000, right? But with the shift in how you compute, things can shift again, right? As I mentioned earlier, there was a paper already shown that branch predictor doesn't perform as well anymore with serverless computing and the way cloud computing is going, right? So you might see another batch of like, okay, how do we design? How do we architect new things? Before we leave today, right? First of all, I want to make sure you are aware that I'm gonna go through the example in detail. It requires a little bit of time, so I want you to kind of like digest the content this week, and the next week in the beginning when we do the recap, right? I'm gonna go through the example just for the two-level prediction. Because the two-level prediction can be complicated to follow. So I'm gonna go through the example. Before we leave today, one thing, last week paper, any thoughts? since I think both of you are reading that, I kind of want to get like feedback from both of you and kind of like open up the floor for like maybe 5 to 10 minutes and see what you think about the paper that you read.
So, sir, actually, the last week paper was that the ISAs must be open sourced, and it actually compared different ISAs, and it concluded that RISC-V is the best ISA that can be open source or that can be utilized nowadays. It compared CISC, RISC, and RISC-V ISAs, and it predicted on some factors like 32-bit address capabilities, 64 address capabilities, and it also said that there must be 128-bit address capability that is present in RISC-V. Yes, there are many other factors in that paper, and well, what I wrote in the pros and cons was that there needs a proper ecosystem. Like Intel is working on six ISA for many years. ARM is working on RISC for many years, and the softwares have adapted or optimized according to that ISAs. So, well, using RISC-V as a global ISA or open source ISA, it will take a lot of time to build that ecosystem or to optimize that softwares according to that. So, yes, this is my thoughts about that paper.
Okay, cool. So let me kind of recap. Like, so that's a good summary of the paper. A few things that you missed about the motivation behind RISC-V. By the way, it's called RISC-V, not RISC-V. The V is like a Roman numeric.
Yes.
So RISC-V is motivated by the lack of open and free. So open and free is two things, right? Open means I can take a look into the code. Free means I look into the code, I want to use it, I don't have to pay money for it. So it's motivated by the lack of open and free ISA. Because if you want to run a startup company, right? And your company, basically, for example, you want to just build chips that do machine learning. And that only. And you want to integrate the chip into another SoC, system on chip, or a different motherboard, right? For another different company that give you mobile phone or self-driving car, right? You kind of have to rely on a few things. You either buy someone else's ISA and pay money to use their ISA. For example, if you use x86, then that's currently the 64-bit version is owned by AMD, right? That's why it's called AMD 64. It's the extension to the Intel 32-bit. And now everyone uses the AMD 64 machine. You can use the ARM ISA, which then you have to pay. Well, ARM was now bought by NVIDIA, right? So you then have to pay NVIDIA for the ARM ISA. Or you can come up with your own ISA, which is a big a big effort, where if you want to run a startup company, it's likely that you won't have the funding, right, to do multiple things at once, right? So if you want to do extension to x86 or ARM, the company has to pay money for that. And the motivation behind the paper is this kind of discourage research into shipbuilding that requires ISA changes and spin into a startup, right? So the team, right? If you look at RISC-V right now, let me actually pull it up. So if you look at RISC-V right now, it's a consortium of researcher and company, right? That work together essentially to how should I put it? To put together both definition of RISC-V, implementation of RISC-V on different types of processor, and how should we extend, right? How should we extend RISC-V, right? And if you kind of look at it, right? I'm not sure. Have you heard about this guy called David Patterson?
Yes,
So David, yes.
Yes, I actually, when I see the author, I actually search for that, and it was the same guy who coined the term risk and work on the risk project as well. And there are a lot of lectures like in Stanford or University of Berkeley online in the YouTube. The guy is giving lectures on the risk history and presenting the same paper that you gave us to read, and the same idea that why risk 5 should be free.
Right. Okay, cool.
Yes.
So RISC-V is actually a collection of multiple senior, right, academic researcher on the architecture area. And one of them is David Patterson, who's kind of like a leading this project from UC Berkeley. He actually with John Hennessy got the Turing Award, which is basically considered like a Nobel Prize for computer scientists and anyone who work on computer, right? On the foundational work in architecture, including the ISA and RISC. John Hennessy and David Patterson wrote a seminal book. It's like you take ComArch class, there's a 90% chance you read his book, right? This is that he make that much impact. So what he think at Berkeley, and actually I was at the talk when he was visiting CMU back I think 6 or 7 years ago. He came by CMU and give a talk on why RISC-V has to be made, right? It's kind of motivated by the lack of hardware startups because of this limitation, because it takes so much of the cost or the funding from the startup company to actually license things like x86. So he wanted to design something extendable, something that's adaptable. So RISC is a good option in the sense that it's not complex. So if you want to build the hardware for RISC-V, you only have to support the core element of RISC-V. Then you can extend that afterward. You can extend that afterward for whatever products you want to launch. And with the extension, it should work on your chip. But when you integrate the RISC-V with other chips that also use RISC-V, it should work because the base of RISC-V is the same. So the hardware would still support the program that utilize some of this extension, right? So it allows more on the tighter integration of research and engineering. And this is like one of the prime example of how I would love to convince many people that research, publication, engineering, and innovation can be integrated and make such an impact, right? So since you are DADs, you might have heard from other professors saying, hey, why is Arkan doesn't publish a lot? They might say, hey, because we work with company and they don't want to publish, they want to patent the idea, right? But you can see from this top company and top institution, there always work required that can be open to public and also work with startup company, technology, and innovate together, right? So that's a great paper that you pick up, and I am glad that you pick up most of them. I just one thing that I want to point out that's like one of the key motivations is about open and free, open and free. The second key to motivation is about making it risk so that you can have a easy time to implement the backbone. And then if you want to extend it later, then you can design whatever fancy things that the startup company can design, right? To be honest, I think many tech companies, for example, in China, that are starting to say, hey, let's build chips, right? They are also picking up on RISC-V as well. So there's another up and coming ISA that I have a gut feeling that they're gonna make a lot of impact in the in the near future, to be honest, right? It's within like 10 to 20 years, there'll be more and more of these things. It takes time. These things take time to have the foundation, right? And if you see element of research, the time it takes to actually translate to actual products, right? You can look at, for example, mRNA vaccine. These have been in research for 10 years, 10 plus years. And you can see the impact it's making, right? Not just the COVID vaccine. People are looking into like using that to treat HIV as a vaccine, thinking about, hey, maybe you can use this to treat cancer because it's a totally new technology, right? And that's how you can kind of like look at motivation from this paper, learn from it, and build something awesome out of that. And that's kind of like the importance of research and the importance of foundational research. These are really important. It's not just giving you the knowledge, it's giving you the backbone of what to do with the technology and how to go forward. All right, by the way, thank you so much. Opat, what did you read?
Can I just ask
Yeah,
one
sure.
more question? You said that there is a difference between risk and risk 5. Can you please explain a brief summary of the differences in that?
So risk is just a generic term that stands for, so let me write it out, right? Right. This is reduce instruction ISA.
Yes.
Right. So this is a generic term that say these are the type of ISA that I would classify as have the backbone of the specification to support basic command like add, subtract, multiply, XOR, jump, branch, and it won't have the elements of the sys ISA where it contains instruction that would do the loop for you or repeat certain things for many times or like write result into an array or things like that. So it would contain just enough so that the computer would function properly. The benefit, so there's a kind of like a mini war going on between people who think risk is better than sys or sys is better than risk, right? So for people who said risk is better, they typically would argue, right? Which, to be honest, I do agree, that once you have the basic functionality, right, the compiler can compile the program to this particular ISA and do the optimization. Then, because you don't have to implement so many instructions, you don't spend the transistor on those instructions that you get to use 1% of the time or 0.1% of the time, right? Then you have extra transistor for optimization like fancy data forwarding, fancy branch prediction, fancy cache, fancy register file, right? So that you can make the computer faster, not by having lots of instruction, but have lots of microarchitectural changes to make each instruction truly faster. So that's the argument from the risk side of things. From people who design CISC ISA, they will say, hey, but there's a lot of common instruction like loading things in your array, right? If I expose that to the programmer, I expose that to the compiler, they can use that instruction. And by default, if you have an ISA for that instruction and the hardware for that is going to be faster than a generic design that would make everything faster, right? Making one thing faster is likely to be better for that one thing than another design that kind of try to make everything faster, right?
Right.
The RISC-V ISA is one of the ISA that has the motivation behind RISC. So RISC-V is one ISA. RISC is like a terminology that governs any ISA that is reduced instruction set ISA. So that's the difference. Yeah.
All right. Thank you.
Okay. All right. So Opa, so which one do you read?
I read in week 2 it only one paper. Can I discuss in week 1 paper
Yeah, sure.
review?
Yeah, yes.
Okay. In we want I will the requirement of bottleneck and code fortune agent for microprocessor evolution. Yeah, this paper is mainly talk about the architecture of the microcontroller and how it everything working together, or just and this paper mentioned about the bottleneck of the development of the microprocessor development. It is about the three things that I yeah it's a sorry in the in instruction supply, how do the microprocessor supply the instruction and working with the program that the developer write. And second is how to supply the data, because of if you implement in fast processor, you have to maintain the data have to enough for support the instruction. When instruction come and how to send the data or just manipulate the data. And the last part, the main last part is good fortune, or just it's the opportunity for increase the microprocessor performance, such as the increase the transistor when in the future the technology is we can creating the smallest resistor, we can add it more and make it faster, or just find some new material for increase the material property, and my opinion about into improve the sorry, my opinion in this paper, I think nowadays we can produce the smallest transistor, and I think we can create or just add more resistor in share LT cache, because in terms of the to increase the buffer to reduce the latency time for access the memory, that will make it increase the microprocessor performance. That the improved gap that I have, and any idea in the
Okay,
paper.
so if I kind of rephrase this, right? So some of your comments are, for example, part of the summary that you got from the paper, which is perfect, right? Is that, let's say you make the CPU really fast. Sometimes you say we need to make the added component like memory also equally fast. Otherwise, the CPU run way ahead of the memory. And then things will be stuck in the pipeline. It's like, hey, I'm waiting for my data, right? So that's what happened. And the paper so this is one unique thing about this paper is it's not about the idea that are presented in the paper. This is called a position paper that senior researcher. So Yale Pat is like, think of it as like he's a rock star of that area, right? So everyone knows him. Everyone in the area knows him. Everyone outside of the area also know him. He's really famous. So he can make this comments, which actually most of the things written in that paper turns out to be true and turns out to be implemented in motion, right? So what he say is, hey, you should look into things like critical path. If you have multi-threading, you want to speed up that slowest guy. If you look into memory, you want to make sure memory is fast. You can do things like value prediction. You can do things to make sure you can fetch the data ahead of time, right? So that the CPU can have the data and proceed forward while the memory is trying to get, for example, more memory level parallelisms or trying to get a lot of data in parallel, right? So these are some of the things that presented in the paper. one thing I want to critique about your idea, which is I first of all I appreciate that you go out to the comfort zone to like, hey, let's actually put more transistor into the cache, like make the cache bigger, right? It's a good idea, but it also has downside about the other element of caching that you might have missed, which is that's the storage part of the cache, right? You can have a lot of things in there. Let's say you want to have 4 megabytes of cache and increase that to 16 megabytes of cache. That's another element about searching for your data, which involves the logic behind, hey, how do I search? How do I go to my data with that address? So it turns out that when you make this cache bigger, there's also overhead of searching that has to be taken care of. Otherwise, the cache will become slower, right? That's how, if you look at your processor that you buy, right? You go to buy an Intel chip, right? You see there's the multiple level of caching. These days you have 3 levels, L1, L2, and L3. L1 would be the smallest, L2 will be bigger, L3 will be the biggest of all, right? And then you go to DRAM. The thing about size is, if you look at how fast each of these cache are, the smallest would be really fast. The middle one, the L2, would be kind of fast, and the L3 would be slower, right? So that, again, your comment is definitely legit, right? You need to make the cache bigger. You also need to make sure when you search for your entry in the cache, you have a way to take care of the time it takes to actually access your data inside the caching structure, right? I'll make this comparison, right? If I need to search for someone in a room that is just in a house, for example, it would take in almost instant. I can yell inside my house and that person can yell back at me. What if that becomes a big auditorium, right? Then it's harder to find because I don't know where people are. It's like people everywhere, right?
Yeah.
Change that to a concert hall, another level of difficulty, right? You make things bigger, you can store more people, but you then spend a lot of time searching, like, hey, where's that guy, right? So this is kind of like a trade-off between how do you want to integrate the design. And I guess the beauty behind this is like, how do you pick the right trade-off that you hide the downside from the programmer and the program itself when you run, right? So that they think, hey, it's fast, but things that are slow, you make sure they don't impact the program. You either do things in parallel or you implement a different logic on your circuit board, right? So these can be done. These can be done for sure, and that's why I said your idea is legit, depending on how you do it, right? So yeah, awesome. Both of you on these comments. So I'm gonna basically, whenever I have time at the end, I'm gonna basically let's kind of like go through this and discuss, like make it more open end, right? And by the way, when I make this open end, whatever I say, partially is my own opinion. So don't treat that as fact, because things can change in unless it becomes law or like it's been proven mathematically that's correct, right? These are my gut feeling. This can be my opinion, but it's good to have discussion because that's how we advance technology, right? So a few more things I want to kind of point out, class related thing. I want to have a project proposal due in 2 weeks, if possible. No write-up requires. I just need a little bit of in-class presentation, like at minimum 2 slides. It's okay, as long as you tell me what you want to do. Most of the content here would be focused on how to frame your project and how to design what's the goal of your project. So it's not too hard or not too easy, right? So not next week, but after, we will spend maybe 15 minutes at the end of the class talking about your project so that we can figure out, okay, what should you do for the project? How can I proceed and what can be done? Nope. Sorry, copy and paste error from last year. Lab 2 is now out. So I changed the lab 1 deadline because I released it way earlier. So I pushed the lab 1 deadline earlier based on the release date, because from last year I realized there's not enough time for the project. Because lab 2 takes a lot more time, so I give you guys a lot more time for lab 2. So you can have the time to process lab 2. And lab 2 is to extend lab 1 to include the 5-stage pipeline. So you do pipelining, and then you check for stalling condition, and you do data forwarding. So once you have data forwarding, you have a fully functional microprocessor that can run single thread. And the project proposal slide, these are the minimum. Let me know what problem you want to work on, because without this, it's not a proposal. Like, I have no idea what you want to work on. Tell me why you want to work on that. And tell me what's your potential solution. For example, you read certain papers or certain report or certain blog posts about, oh, you can do this thing to make it faster, or you can apply these techniques. Let me know so I can have an idea or rough estimate of, is this doable? And is this technically challenging, so that you have a right difficulty for the project? Not too hard, again, not too easy, right? I'm not asking you to do a new thing. This is not research methodology, or this is not actual research. You can re-implement certain things that are challenging or fun for you, right? And make sure you have a different goal for your target, like 75%, 100%, and 150% for your goal, so I can adjust it accordingly. Because if your project is too hard, your 100% goal should become your 150% goal. If it's too easy, we have to talk, because we have to kind of figure out what's your 100% goal, what's the full expectation from the project, what's partial expectation of the project. Another thing is, once you finish lab 3, you can use that feel free to use that as a starter code. I have so basically lab 3 would extend lab 2 to include more things we learned, right? But you can do other powerful things like modeling the main memory, or modeling the cache and the main memory, or modeling things that you want to model. These are not as recommended for both of you, because it seems like both of you have something in mind what you want to do for your master thesis. So ideally tie that to your master thesis, so that you don't have to put in extra effort for the class, right? So that you can kill 2 birds with 1 stone, essentially, right? So in 2 weeks, we'll have this. Next week, I'm going to go through the example about branch prediction for the GHR and the LHR. And then we'll start to dive into the next concept called out of order execution. And once we're done with out of order execution, there'll be a midterm. This is like the next, probably 3 or 4 weeks. We'll see where we are around that time, and I'll let you know. So don't panic yet, right? Don't panic yet. And that's the end of the lecture today. Any questions?
Sir, I actually have question not from the lecture, but a term used in week 3 paper. Can I actually ask that?
Share the screen so that you can show me the actual
paper?
Yeah.
Okay, sir.
Let me unshare my screen quickly so that you can share. Okay. I think you should be able to share now. I'm just going to transition to my desktop as well, so I can take a look at in a much bigger monitor. I'm going to leave from my laptop and turn on the volume of my desktop. All right, can you hear me?
Yes. Can you see my screen here?
Hello, can you hear me?
Yes, we can hear you.
All right, the speaker is not on. let me figure out what's wrong with my speaker. Oh, can someone say something? I just muted my computer
yes.
by accident.
Yes.
Hello, can someone say something?
Yes, we can hear you.
Oh, someone already said something. I cannot hear anyone. Let's see. I guess I'll use my headphone.
Okay.
All right, so test.
Yes.
Yes, perfect. I can hear you.
Yeah.
Okay, so what's the question?
Can you see my screen?
Yes.
So this is the paper validity of the single processor approach to achieving large-scale
Mhm.
computing capabilities. You were just talking about this, and there is a term coined in there. This is data management housekeeping.